right, now we begin. This belated session is being brought to you by the fractal globe snow ring. All right, we proceed. All right, now I begin again. Today we start on vectors. This is a concept from physics and engineering, very useful there. It's a displacement between points, from the initial point to the terminal point, from here to here. It's the displacement, not the place. Here are a bunch of vectors which have different initial and terminal points, but they're the same length and the same direction, so they're called equal. These vectors are in this different direction, so they're unequal. These have different lengths, so they're unequal. A vector from like this will have a horizontal displacement of A and a vertical displacement of B, and it's therefore denoted pointy bracket A to B pointy bracket. A is the x coordinate, B is the y coordinate. These are rectangular coordinates for a vector. If it's pointing from x1, y2 to x2, y2, then its coordinates of the vector are x2 minus x1 by y2 minus y1, a displacement between points. Given a vector A by B, its length is denoted by putting two brackets around, two vertical lines around it, like an absolute value sign. The length of a vector is square root of a squared plus b squared from the Pythagorean theorem. We can add vectors this way. If we have a vector v and a vector w, we start them from the same initial point. Draw vector v here, draw vector w here, then complete this parallelogram with this vector w parallel and equal to this one, this vector v equal to this one, and from this initial point, shared initial point, to this shared terminal point spans the vector u plus v. That's geometric definition of adding vectors. The algebraic definition is that you add coordinates. A by b plus big A by big B is A plus big A by b plus big B. So you add them in parallel. And if you can rescale vectors, if you have a vector v, then here's the length v, 2v, twice as long in the same direction, a half v, a half as long in the same direction, and minus v, as long in the opposite direction. That's the geometric definition of rescaling a vector. Its algebraic definition is k times a by b is ka by kb. Again, everything happens in parallel, in separate coordinates. You add separate coordinates and you multiply separate coordinates. Now, we call it addition because it has many of the same rules as addition of numbers. It's commutative. U plus v equals v plus u. It's associative. U plus v plus w is u plus v, that plus w. There's a zero vector, 0 by 0 of zero length, and I suppose any direction. U plus a zero vector equals a u vector. U plus its opposite, pointing in the opposite direction, equals a zero vector. It has distributivity of a specialized sort. K times u plus v equals ku plus kv. Please note that this is what is called scalar. This is a number, a scalar, and you multiply it, and this is a vector addition. So scalar multiplication distributes over vector addition. And here the other way around. K plus h times u is ku plus hu. So here we have scalar addition. It's distributed over by scalar multiplication. And here scalar multiplication is associative. K times hu is kh times u. As long as the k and the h's are numbers, then these distributive and associative laws work. We will discuss multiplying vectors, but that will in the next sections, but it's not quite the same thing. Now, here's a vector in the unit one unit in the x direction. It has coordinates 1 by 0. This is called the vector I. Here's a vector 1 unit in the y direction, coordinate 0 by 1. It's called j. And any vector a by b equals ai plus bj. AI will be a by 0, bj is 0 by b. You add them and you get a by b. So those are polar coordinates. There are also rectangular coordinates for vectors, as follows. So here we have a vector. It has a certain length of v. It has an angle theta from the horizontal positive direction. positive x-axis. Then it's easy enough to see that v is equal to length of v times cosine theta plus by sine theta. This is called the unit vector in the v direction. It also equals v divided by its length. This is a lot like r cis theta we saw the last time for complex numbers. And in a sense of complex number is a kind of vector with some additional structure. Now we have some rules. Here we have length of v is 14 and it has an angle of 120. What is v? What are its coordinates? Well, length of v times cos theta by sine theta, that'd be 14 times cos 120 by sine 120. Cos 120 is minus a half, sine 120 is 3/2. Multiply each of these by 14 and you get negative 7 by 7√3. That's in coordinates. In terms of I and j, it's negative 7i plus 7√3j. So here's some more examples. Here's a vector from -2 by -1 to 6 by -2. What are the coordinates of the vector? Well, difference of the x value is 6 minus -2 by -2 minus -1 here. And this comes out to 8 by -1, and that's the vector v in rectangular coordinates. What is the length of the vector 3i minus 4j? Well, it's the length of the vector 3 by -4. And then we use the Pythagorean relation. Its length is root of 3 squared plus root of -4 squared. So root of 9 plus 16, which is root of 25, which is 5. Really, this is a 3, 4, 5 triangle. Here we have a vector. Here the length of the vector I minus j. What's that? Well, I minus j is 1 by -1. The length of that will be root of 1 squared plus -1 squared, which comes out to root 2. Now you're going to have some vector arithmetic. V is 3 by -5, W is -2 by 3. What's 2u plus 3w? What's the length of u minus of w? What's the length of u minus the length of w? Slightly different here. 2u plus, so here we go. 2u plus 3v. 2 of this, 2 times 3 by -5 plus 3 times -2 by 3. Multiply 2 by each of these and you get 6 by -10. Multiply 3 by each of these and you get -6 by 9. Add them, we add components. -6, 6 minus 6, -10 plus 9 comes to 0 by -1, aka -j. Length of u minus w is length of u minus w, 3 by -5 minus -2 by 3. We subtract components. 3 minus -2 for the x component, -5 minus 3 for the y component. That comes to 5 by -8. So the length is root of 5 squared plus -8 squared, root of 25 plus 64, which is root of 89. Length of u minus length of v. Now the length of u is length of 3 by -5 minus the length of v, length of -2 by 3. Length of 3 by -5 is root of 3 squared plus -5 squared. That minus length of this is root of -2 squared plus 3 squared. Here's root of 9 plus 25. This is root of 4 plus 9. It's root 34 minus root 13, which is in no way even at all like this. So length of the difference and difference of lengths are, as we see, quite different in this case. Now here we have u is 25, the v is 25, theta is 330. What's v? What's the vector? Well, it equals 25 times cos 330 by sine 330. That comes out to 25 of root 3/2 by -1/2. Multiply each of these components by 25, and you get 25 root 3/2 minus 20 by -25/2. Now, this last one is where we get into practical engineering. Einstein said that where the laws of mathematics are certain, they don't apply to reality, and where they apply to reality, they're not certain. So always there's a little bit of fuzz when we're dealing with engineering. Here we have a 1,000-pound weight being suspended by 2 cables. One canted downwards at 40 degrees, and the other canted downwards at 25 degrees. That doesn't sound like a very efficient way, although it's probably stable under left-right oscillations. What are the 2 forces on the 2 cables? Well, for this, we have to use a principle called equilibrium, which is if you add up the forces on this, Because it's at equilibrium and not accelerating in any direction, the forces must all add up to 0. Now this 1,000-pound weight gives you a 1,000-pound force force downwards, and its vector is denoted as 0 by negative 1,000. Here we have F2 pointing upwards. The force on the weight is upwards at an angle 40 degrees. F1 force is upwards to the left at an angle of 25 degrees. Now, okay, if this is 25, then this supplementary angle is 155, and we'll work from that coordinates. F1 plus F2 plus this 0 by negative 1,000 equals the 0 vector. That's a static equilibrium rule. All right, so we'll start from here. Now, F1 is a force of, F1 at an angle of 155 degrees. So it's F1 cos 155 by F1 of sine 155. F2 is a force of F2 at an angle upwards to the right of 40 degrees. So its coordinates are F2 cos 40 by F2 sine 40. So F1 plus F2 plus 0 by negative 1,000 equals the 0 vector. Here's F1, F1 plus F2 x coordinate, F1 plus x2 y coordinate, 0 vector. We add these, F1 cos 155 plus F2 cos 40 plus 0 for the x coordinate. For the y coordinates, F1 sine 155 plus F2 sine 40 plus negative 1,000 here, and that equals 0. So this by this equals 0 by 0. Vectors are equal if their components are equal. I guess I should have mentioned that earlier. But okay, so this F1 cos 155 plus F2 cos 40 equals 0, as in here. For this one, F1 sine 155 plus F2 sine 40 minus 1,000 equals 0. So I rewrite that slightly as, yes.
Oh, I'm so sorry, Professor. I didn't mean that.
Okay, it's all right. Actually, I really would like it in the course of classes if people raise their hands more often. So,
Yeah.
do you have questions? I'll be willing to answer.
Okay, thank you.
We proceed. So here we have a 2 by 2 system. F1 cos 155 plus F2 cos 40 is 0. F1 sine 155 plus F2 sine 40 equals 1,000. It's a 2 by 2 system. And we've gone over solving 2 by 2 systems. We use elimination, substitution, Kramer's rule, what have you. And we get, after considerable calculation, which I'll skip past because that was from a previous class, look at the F1 is 845.2 pounds and F2 is also 1,000 pounds. So it's like all the weight has gone into there anyhow. So that's the engineering calculation for the forces on these two chords. I suppose it's more it's better to have it like this because it makes it less like to sway left and right. Although I suppose you really should put a third cable to keep it from swaying backwards and forwards. Okay, that's these. I believe we have completed the. I believe we have completed our the day's work. Okay, yes, I did press record. Thank you. Yes, in fact, turn it off.